You've heard me talk about throwing a baseball up in the air and the time at which it's like, 8 feet high or whatever, and you guys have gotten comfy saying, oh yeah, that'll be a couple of times, right? Because it's going up and then it's coming back down. So this is a similar situation that we've got here with Dennis. Dennis is throwing a ball from the top of a building, okay? Now, in this case, he's up off the ground quite a bit. So the first thing that I would recommend we do on a problem like this, you and I are going to work this one together, is I would just, draw a little picture. Here's the top of the building. Thank you very much. And here's the top of the building. Here's Dennis. And he's going to throw that ball. And it's going to hit the ground. Okay? Now, that's nothing profound, but what that does is that helps me visualize what's going on in this scenario. It says he throws the rubber ball from his hand 80 feet above the ground. So this height right here is 80 feet. Okay? And it's modeled by this height function. And what type of function, Justin, is h of t here? What type of function is that height function? Remember how we practiced classifying?
Oh, that's silent.
It's not linear. Help him out, Drake. It's a degree 2. What do we call a degree 2 function? Either Bowers. It is quadratic. Good. Quadratic, right? Quadratic function has how many zeros? 2. It has 2 roots, 2 solutions. We know that from our fundamental theorem of algebra. Okay, Nick, thank you for taking care of that for me. Now, it says the zeros of this function, which tells when the ball hits the ground, that's the first thing that we want to do. So all we're going to do is we're going to set the function equal to 0. We're going to say we want to find what is t when h of t equals 0. Okay? And you guys have practiced with me solving equations like this. It's already set equal to 0. So normally I would factor in to use the ZPP, use the zero product property. Calderoni. I would recommend doing exactly that. If you didn't hear what he said, let me reiterate it for you. He said, hey, that leading term, that leading coefficient, I notice it's negative. Let's make it positive. Now, why would we, Calderoni, why would we do something like that? Yeah, we're used to factoring things where that leading coefficient is positive. Okay, now I happen to know that 16 goes into 16, 64, and 80 as a GCF. So why don't we do this? Why don't we we saw an example like this yesterday. Why don't we factor out negative 16? Okay, Joseph Russell, tell me what's left over when I take out a negative 16 from each of those terms. All right, t squared. So you're mentally dividing each term by negative 16. Make a guess. What kind of 4? Negative 4t. All right. And if 16 times 4 is 64, what do you think 16 multiplies by to give you 80? Hey, Wayne. Negative 5. That a boy. So negative 5 would be exactly right. Okay, so now, Cash, we look at that trinomial after Joseph took out our negative 16. We look at this trinomial and we think, hot dang, that's easily factorable. That's what we call our regular trinomial. So go ahead and factor it out for me. I want 2 parentheses. And I'll spot you a t up front on each of them. Okay, 2 factors of negative 5 that add up to negative 4. What are they? Cash is on the hot seat here. Go ahead, Cash. Negative 5 and positive 1. Good. You already knew that before he said that, though, right? That a boy. All right. So, fellas, that means that I've got these 3 factors. I've got negative 16. Is negative 16 ever going to equal 0? No. No. That's the bathwater. Throw that out. That's not. There's no skin off my nose if we divide both sides by that constant. We saw that yesterday, right? Because we said that it would produce an equivalent equation, and the graph of that parabola, right? If you looked at this curve as opposed to this curve, they're both going to have the same x-intercepts. One of them is just going to look like this, and the other one is going to look like that, okay? Where they both hit the x-axis at the same spots, and we're just concerning ourselves with the easier one, as Santiago said a moment ago. And what would be my two answers then from this quadratic equation? Okay. Now, Wilson Webster, which one of those is the extraneous solution? We used that word in yesterday's class, correct? We talked about the extraneous. It's an answer that you got, but it doesn't make sense in the process, so you throw it out. So which one, Wilson? -1. Why is that the extraneous solution that I should throw out? Yeah, I mean, Dennis is not a time traveler. Last time I checked, okay, he's not going in negative time back to -1 seconds, okay? Yeah, but t is time. So what we're just answering is we're saying, hey, we want to find the zeros when this ball is going to hit the ground. So the ball is going to hit the ground in 5 seconds. So he throws the ball up 1, 2, 3, 4, 5, and then hits the ground. Okay. The way that we modeled it was with a quadratic function, and that model doesn't make sense for a negative t value because you're modeling height in terms of time. Okay? Cash. Yeah, yeah. At home, my kids keep, oh, that's chalk. You don't want chalk. My kids keep a buttload of these like little rubber erasers, you know, those big fat pink ones that you guys probably have seen. And I wish I had those up here because I got a bunch of them. But this should work for you.
You gotta get all that cap off the paper.
Now, what we just answered was the first question, part A. It says, what about when the ball will be 80 feet above the ground? How, Colton, is that going to make my process any different from what I just did in green? Absolutely. If you didn't hear that, he said, well, just do the same daggum thing. Set the function, instead of setting it equal to 0 to find the zeros, we're going to set the function equal to 80. And again, how many solutions will that have? That quadratic equation will have 2 solutions. All quadratic equations have 2 solutions, don't they? Excuse me. So we got 80 equals -16t squared plus 64t plus 80. What should I do to both sides? Good. Subtract 80. And let's just start rolling with it. -16t squared plus 64t. If I subtract 80 from both sides, that constant term goes away. And then the problem works very similarly. All right, we could factor out a -16t. All right, and we're going to be left with t minus 4. Here, this is t equals 0. And here, this is t equals 4. Okay, see how I went through that pretty quickly, pretty rapidly? We got our 2 answers. Now let's see. Does that first answer make sense? T equals 80, or excuse me, t equals 0 is a time at which the height is 80. Does that make sense? It certainly does. Look at the picture. Right before he releases the ball into the air, right? Time is 0, and the height of the ball, we're told, is 80. That makes sense. It's kind of trivial, though. It really doesn't matter. What we were more interested in is it says, when is the ball going to be 80 feet above the ground? So look at my picture here. Check this out. Here's one point in time where the height is 80, and then the ball goes, woo, and it hits back at that same height, that same horizontal level again, after 4 seconds. That means that it took how many seconds to go from here down to the ground? Good, William. 1 second. Because we had solved in the previous one and we knew it took 5. Ooh, right there. All right, Mr. Perone, question. No, good question. Let's play that game out. Let's see how that would work. So if we just took out -16, we'd have t squared minus 4t, right? At this point, I would divide both sides by negative 16, right? Just because that's throwing out the bathwater, not the baby. So t squared minus 4t. And then you would just say, okay, you know, that's a GCF of t. Let me take out a t. And I got t minus 4. Okay, and again, you're going to use your ZPP and get t equals 0 or t equals 4. So either way you want to slice it, you could do it either way. All right, great question. So this, hopefully, is this problem making some good sense to us, how we operate with quadratics when we're trying to figure out what we set them equal to 0 when we want to find the zeros. We set them equal to, like in this case, 80 when we're asked about 80. So we said, you know, 0 seconds and 4 seconds. What do you think I need to do on part C? What do you think I should do? Hand in the air if you think you're a player here. It says the height of the ball at t equals 2 seconds. Go ahead, Luke.
So at C,
Part C. You raised your hand. You tell me, how do I find the height when t equals 2?
oh yeah, when it, I know I answered now.
That's okay, Drake.
Would it be like the vertex part, like the highest part?
Now, that's an interesting question. We will talk about that vertex in just a minute. But I don't necessarily know if after 2 seconds that has, I kind of have an inclination that it might be. But we can't assume that it will be the vertex. But even so, that doesn't answer the question that they asked. They said, hey, how high is it? Quinn, how do I find how high it goes? Yeah. H of t is a function that produces the height at time t. So if I want to know the height at time t equals 2, I just plug in h of 2. And I think, Kreitz, that's probably what you were going to say, right? So help me do that, William. We got negative 16 times, can you go ahead and square the 2 for me and then multiply it by the 16? What kind of 64? Good, because that 16 is a negative coefficient, right? Let's see here. And then 64 times 2 would be, good, 128. You're helping me with my arithmetic. Thank you much. And then we got plus 80, which is not affected by the time at all. So that's going to be 64, so 144. You guys tally with that? What's 64 and 80? Is that 144? Y'all's silence is making me a little nervous.
Yeah.
All right, so 144 feet is how high that ball gets at t equals 2 seconds. Now, we don't necessarily know just yet, but Drake has been, you're barking up the right tree when you think that's perhaps is going to be the highest height that it is. It's the vertex. Now, again, there's a difference between A and B and in part C. Which one did you guys find to be a little easier?
I thought the first
I'm shocked by that. Usually part C is the easiest part here. Just plug and chug. Just do arithmetic, okay? There was no solving. There was no factoring. There was no ZPP business. It was just, we'll plug in t equals 2. We'll plug in t equals 3. We'll plug in t equals 3.6. We'll plug in t equals 7. You know, whatever. Time that gets plugged in. There's a difference between input and output. On part C, we were given our input, and we were asked to find our output. That is a relatively straightforward operation when you know what the function is. Okay, the hard part is finding the input to match your particular output. Okay, in other words, it's easy to solve for x. It's hard to solve for. It's easy to solve for y. It's hard to solve for x. But here's what I wanted to do. I wanted to take this equation right here. And actually, let me just snip this. So we'll not have to rely on my lousy memory here. All right. Copy. We're going to paste. All right. So we've got h of t equals negative 16 t squared plus 64t plus 80. That's what I wanted right there. Now, you guys, on your notes or in your notes, write that down and kind of have some space up underneath there. We're about to do we're going to dive deeper, okay, into this parabola, into this quadratic function. Now, first thing I want to know, and we'll throw this over to Hogan. Can you talk to me? Is this field goal is good or is this swole patrol? What do we got? Is it concave up or concave down?
Concave down.
It is concave down. Your vocal intonations make me think you're kind of guessing at that, though. How can we be sure, Nick, that this is concave down, swole patrol?
I was just going to ask, well, we know it's concave down because there's a negative right front.
The leading coefficient test. When that leading coefficient is negative, we know that it is going to be concave down. Go ahead, Nick.
And is that a 69 or 64?
64. 64. All right, so we know this guy's going to be concave down. We just found a couple of its zeros. Y'all remember what those zeros were? -1 and +5. Are y'all sure it was +5? Oh, I'm remembering the one in orange. That's right. All right, it's concave down. It's zeros. Now, what's another way of saying zeros, graphically speaking? What did we find about the parabola when we found its zeros, its roots? It's x-intercepts. Good. So it's concave down. It's got x-intercepts at, what'd y'all say? -1 and 5. We haven't talked about its y-intercept yet, have we? Can you easily tell me what the y-intercept is? It is 80. Very good. And the y-intercept is easier to find than the x-intercepts. The y-intercept, you could use the cover-up principle, right? Because that's like plugging in t equals 0. All right, so we've got 0, 80. All right, now let's put all of that together in a picture. Let's put all of that together in a picture here. Okay, there's 0, 80. Here's, whoops, I'm leaning on my keyboard. Here's 5, 0. And here's -1, 0. Now, right now, how many points I've got is just 3. To graph out a good parabola, we want to try to get more than 3 points, okay? We want to try to find, what was that V word that we used a minute ago? We want to try to find the vertex. Now, you guys are smart, and you're very capable, and so I'm going to describe for you a couple of ways that you could find the vertex. One of them is a visual way that's based on symmetry. Do we remember talking about symmetry the other day? I think I referenced an episode of The Office, maybe. Talked about Hillary Swank. Okay, so remember, symmetry is where it's the same on both sides. And there's that, what's that line called, that imaginary line that we draw down the middle? The axis of symmetry. It's going to split the difference between our x-intercepts. So you tell me, where should I draw my axis of symmetry? Where should it pass through the x-axis? William? Very good. We just split the difference. Y'all know what I mean by split the difference? Cut it in half, bisect it. So if there's 6 units between these two x-intercepts, then I know 3 is going to be halfway, and that's going to put me right there at x equals 2. Okay? Or t equals 2 if you want to call this your t-axis. Okay? So our axis of symmetry we can sketch right here is going to have the equation x equals 2. A vertical line has an equation of x equals a constant. Okay? Now, going back to that idea of the vertex, now we know where its x value is. We know that somewhere on that dotted red line is the highest point of this swole patrol parabola. Now, how high does it go up? In other words, what is the height when h, or excuse me, when I labeled that x, I'm going to go back and call it t just to be consistent. And we'll call this our t-axis, and this is our h. This is our h-axis, okay? Height as a function of time. How high is the ball at time t equals 2? 144. Now, how'd y'all know that already? No, I didn't tell you anything. We found it by doing what? By plugging in time t equals 2. In other words, if you know the input, you can easily find the output. And that's 144. All right, now, up to this point, we didn't necessarily know that was going to be the highest value. But now we do. 2, 144. We know that's the highest value because it's the vertex. Okay. Now a parabola is symmetrical. All right. So let me actually scooch this over. I kind of put that in the way. That y-intercept, its coordinates are 0, 80. It's symmetrical. So if I'm going to sketch this parabola out, and this is not a super pretty curve. I apologize that it's not so awesome, but that's all right. It's real tall and narrow. I told you guys I like to have more than 3 points. I've got 4 points right now. Really, you can make a 5th point just by mirroring symmetrically over here at that same height. And one of you guys tell me, what do you think the x-coordinate of that other point would be where the height was 80? How did you already know it was? What is it? Orange. So the height, remember part B when we answered the question, when is the height 80? Right? 0 and 4. So look at what we found over here. 0 was this point right here. And then the other one is going to be 4. Now we knew that from having already done the work. Or we could say, hey, look, there's a space of 2 from the axis to that first point. So therefore, there must be an equal space, a symmetrical spacing of 2 going over there. Does that make sense visually, what we're doing? Okay, so graphing out a parabola is a skill that I'm responsible for teaching you guys. And so let's make sure we know the important points about this parabola. Over here in orange are the important points. All right, 2, 144. We want to know concavity. We want to know x-intercepts and y-intercept. And we want to know where the vertex is. Now, in this class, you and I have already discussed, is it possible to have a parabola without any x-intercepts? What if this parabola had the same vertex, but instead of concave down, it's concave up? No x-intercepts. All right. Its 2 roots, its 2 zeros would be imaginary. You'll talk about that in Algebra 2. Okay. But if you can find x-intercepts, find them. It's going to always have a y-intercept. You'll find it, and then it's always going to have a vertex. So good question. We call a concave up or a concave down parabola, we call it a vertical parabola. Every vertical parabola will always have a y-intercept. That's a good true-false question to be prepared for, right? So like every parabola has a y-intercept because think about what is the domain of a quadratic function. In other words, what values am I allowed to plug in? All real numbers. You're allowed to, in the context of the word problem, I know that obviously that was limited to t has to be greater than or equal to 0. But in the general scheme of things with parabolas, you can always plug in a 0 and get an output. So it will always have that y-intercept. No, not necessarily. What's the most number of x-intercepts that you could have? 2. What's the fewest number of x-intercepts that you could have? 0. Can you have 1 x-intercept?
No.
What would it look like? What's that T word that we use to refer to a curve that touches a line at one spot? It's a trig function also. It starts with T. T. Tangent. My butt is tangent to this table at one spot, okay? Well, there's a line, there's a curve, it touches it at one spot. That's being tangent to. Now that word gets used in a lot of different contexts. You might have heard of sine, cosine, and tangent. Y'all heard of those 3 things? Y'all never did trig in middle school? All right. Anywho, if you're going off on a tangent, then you're going off. Well, what does that even mean? Going off on a tangent. Okay, this is a little calculus for you. Here, suppose that you've got a curve. It just means that, that curve, if that curve is tangent, if that line is tangent to that curve, that means it touches at one spot. But when you hear the phrase going off on a tangent, what that means is that the normal flow of conversation might be going in this direction in blue, and yet here you are going off on a tangent. You're going in another direction, right? That's where that phrase came from. You are deviating from the conversation when you go off on a tangent. So a tangent line touches the curve at this one spot. And if you were to say, Coach, how could you have a parabola with only one x-intercept? That parabola would be tangent to the x-axis. It would touch the x-axis at one spot. Regardless, to get back to Alfred's question, okay, you will either have zero, you will have, I don't know why y'all aren't writing all this down. This is gold, baby. This is gold. You will either have 0, 1, or 2 x-intercepts for every parabola that we study in Algebra 1. A vertical parabola, concave up, concave down, it's either going to hit the x-axis 0 times, 1 time, or 2 times. Okay? And then also keep in mind that it will always have exactly one y-intercept because you can always plug in, x equals 0 or t equals 0 in this case. Okay? You can always do the cover-up principle. A parabola, no matter how narrow it is, it's always scooting outward as well. Look at my hands. It's always spreading outward. I mean, look at this blue graph right here. I could get in my Honda Accord and I could drive a mile down the road in that direction. And then as long as I go down far enough, I'll eventually find where that parabola is. Okay? Every parabola that we encounter has a domain of all real numbers. Okay? So I could plug in t equals 1 billion, all right, and I would get a y value. I'd get an h value, and it probably wouldn't be very useful, but there you go. Now, JT, question.
Oh, you said there was 2 ways upon the vertex.
Yeah, very good. I'm glad you got back to that point. The other way, so like the first way we split the difference, we use the axis of symmetry. The other way is a little bit quicker. Okay, check this out. If we were to consider this in general form, a x squared, or again in this case t squared, plus bx plus c, right? In other words, what's the quadratic coefficient in my little green generalized statement up there? What's the quadratic coefficient? The number in front of t squared. A, good. This is called our quadratic coefficient, everybody. You guys remember that term? All right. Coefficient means number in front of. Quadratic means the term of degree 2. All right. So what's my linear coefficient? What's my linear coefficient? Ashton, I hadn't asked you a question yet. Up there in green. So A is the quadratic coefficient. What do you think the linear coefficient is? Yeah, very good. It's that linear term is degree 1. Again, coefficient means number in front of. Okay, so the way that we find the x-coordinate of the vertex is we look at A and B. Okay, here it is. Your vertex, generally speaking, will always have an x-coordinate or an input of the opposite of B divided by 2A. That is so super important for you guys to memorize that as soon as humanly possible. Okay? In the context of graphing parabolas, that'll make your life a whole lot easier. You can find where that maximum or that minimum occurs just by looking at it. Okay? What was B in this example in black? 64. Okay, so the opposite of 64 is? Negative 64. Good. All right, what is 2 times A in this example? 2 times negative 16, which is negative 32. Good. What's negative 64 over negative 32?
2.
What's the x-coordinate of our vertex, or the input of our vertex? 2. What I'm saying is that we did the opposite is 64 over 2 times negative 16. That's negative 64 over negative 32. That's 2. It is not a coincidence. It is a fact. That's why the vertex had that input of 2. Okay? So what you can do is you can find the input of your vertex without having to worry about it at all. Okay? Doing very little math at all, just maybe a little bit of arithmetic. Okay? Now, we got about 5 minutes left in class, 4 or 5 minutes left in class. And so I'm going to start another application problem, another word problem, if you will. And we might not get to finish it, but I'm going to pitch it to you this way, okay? You got a cube. You guys practiced drawing cubes before? Y'all ever do that? That's not an awesome cube, but there you go. You got one. And you got another cube. So with the power of one note, come on now. One note's not responding. I hate you, one note. There we go. I still love you, one note. Just kidding. You got another cube that's a little bit bigger. Okay? Now, the difference between their volumes is 61. The difference between their volumes is 61. Okay? So obviously the bigger one has more volume, right? Now, there's also a discrepancy between their lengths, okay? This first cube, if it has a side of length x, the other one is a side of length x plus 1. In other words, it's 1 unit larger on all 3 sides. So, you know, if the left side here is x, then the left side here is x plus 1. You guys get what I'm saying? If this length coming out of the screen is x, then this length is x plus 1. Okay, so now you've got all the information you need, okay? You've got the relationship between their sides, and you've got the fact that their volumes, there's a difference of 61, okay? And your job is to figure out what are the lengths of each cube? What are the dimensions of each cube? Now that seems like a really weird rando problem. How does it apply in our context here? Well, first of all, do you know what the volume of a cube is? Good. Length times width times height. And in the small cube, that would be what? X times x times x, which we know as x cubed. That's why you call it x cubed, by the way. I don't know if you knew that or not. Okay. How would you express the volume of the bigger cube? Oh, that's a swift kick in the gonads. Kreitz, I owe you from yesterday. Now I owe Quinn page 1, too. No, you don't just cube the x and cube the 1. It is a what problem? It is a FOIL problem. X plus 1 times x plus 1 times x plus 1. Now, do those two volumes equal each other, or what did I say there was a discrepancy of? How much a discrepancy did you pick up on? 61. So I can either subtract 61 from the big one or add 61 to the little one, and now we've got ourselves an equation, okay? That's not an easy equation to solve because people make, love you, Quinn, no offense here, people make the bonehead mistake that Quinn made a moment ago. Or was it Santiago?
No.
Is that it, like Quinn? Look at him trying to throw you under the bus. You make the bonehead mistake of just saying, oh, that's x cubed plus 1 cubed. Wrong. It's x plus 1 times x plus 1 times x plus 1, which I think Will Perone is grinding out as we speak, which we said was a FOIL problem. It winds up being x cubed plus 3x squared plus 3x plus 1. Now, what type of equation is this? It's not quadratic yet. It's cubic. And how many solutions does a cubic equation have? 3. However, what can I do to both sides to make it really quick and easy? Subtract x cubed from both sides, subtract 61 from both sides, and then wham, bam, thank you, ma'am. Now we're down to a what kind of equation? It starts with a Q, ends with quadratic. It's a quadratic equation. And I'll leave that for you guys to solve, and away you go. You get a couple answers. One of them would be extraneous, by the way. Now, I will not be here tomorrow, so please do a good job for the sub, and make sure that you guys check on campus for your assignment. It'll probably be on Delta Math. Live Jesus in our hearts. All right, thank you, fellas. Y'all be good. I told you that was part of the given information of the problem.
Do we have any homework?
Yeah, it was due today on Delta Math, and then there won't be anything due tomorrow.
Three, okay.
Anyway, all right, Ryan, thank you so much. Take care.